Okay, so in this video, I want to explain what PDF, CDF, and PMF is, which is probability density function, cumulative distribution function, and the probability mass function. I'll also just touch upon what distributions are, and in the next video, we'll actually study these distributions in detail. So before I start, I just want to drive home the point once more of what a random variable is, all right? A random variable is basically, think of it as a function that maps the value of a random experiment. The value of the random experiment forms the sample space, right? So it maps the value of the random experiment, which is a part of the sample space, to a real number. So let's say I perform a random experiment, and I get few outputs over here. Okay, all of these outputs for this particular random experiment, they form the sample space. And what the random variable does is that it tries to map those values to some value. It tries to map a value from the sample space to a real number. Okay, the real number can be anything between minus infinity and infinity. So now that we know this, let's understand what the first I'll explain what a distribution is in general, like in very basic. Okay, so we have a distribution, a very popular distribution called the Gaussian distribution. In essence, what a distribution does is that it helps us model our data set. So if I have a Gaussian distribution will always look something like this. Okay, it'll be big in the middle over here, and it'll be spread around onto the ends. Okay, and it has some very good properties, such as the center of the distribution. You can find the mean of the population, and then one standard deviation away, you'll have 67% of the population just one standard deviation away, one SD, right? And two standard deviations away, you'll have 95% of the population. And three standard deviations, you will have 99.7% of the population. So, in essence, what the Gaussian distribution does is if I have a value, I can get the value and I can get the probability of observing that value in reality. Okay, so let's say this is a distribution, a Gaussian distribution that tries to model the heights of people. Now, the thing is, in reality, for some reason, a lot of things tend to follow the Gaussian distribution. Uh, Heights of people is one of them. The length of hands, legs, or the hair length um, is also another phenomena that tends to follow the Gaussian distribution. So if you have the value over here, you can just plot it and you can get the probability. The probability for that particular value, p of x, is on the y-axis. And on the x-axis, you have the values. So let me just draw this once again. Suppose I have heights, okay, of people. And let's say this is the Gaussian distribution. So in the middle, I have my mean. The mean can be something like 150 centimeters. And then I have probabilities on the y-axis, p of x. So if I have a value x, let's say 160, it falls somewhere here, I can find the probability of observing that value, which is 160 centimeters, in real life, if I extrapolate it on the y-axis, right? So this is the Gaussian distribution. So now this is a continuous Gaussian distribution because height of people is a continuous variable, right? You can have any real value between some range like 120 or 180 and stuff like that. But what if your distribution is not continuous? What if it's discrete, right? In that case, we have something called the probability mass function. So let me just take an example here for the probability mass function. Let's say I am a bank and I want to find the number of genuine and fraudulent transactions. Okay, the probability of observing a particular number of genuine and fraudulent transactions. Let's say there are four variables. Just for simplicity's sake, let's say that uh, the outcomes can be genuine, fraudulent, or genuine, fraudulent, or genuine, right? Um, so let me just draw a table over here just for explaining. So if I have the probability x equals xi over here, and over here I have the number of fraudulent transactions. Okay, so let's say that the number of fraudulent transactions is equal to 0. The probability of observing it is 0.2. The number of fraudulent transactions is equal to 1. The probability of observing it is 0.15. The number of fraudulent transactions is equal to 2. The probability of observing it is 0.25. Similarly, 3 is 0.25 and xi equals 4 is 0.15. I hope you understood this. So what I'm trying to do is I'm trying to model the probability of observing a fraudulent transaction. And this is easy to say that it's discrete, right? Because you can only have a particular fraudulent transaction. You can either have 0 fraudulent transactions or you can have 1, 2, 3, 4. You can't have 3.5 fraudulent transactions. That doesn't make any sense. So, what the probability mass function does is that it helps us find the probability of observing a particular value. So over here, I've given you the probabilities. Right now, if I want to find uh, like 2, the probability of observing that I'll have less than or equal to 2 fraudulent transactions. Okay, I can just take the sum of all of this. Because you see the sum over here is 1, right? All of these values, the sum is 1. So the probability of observing a fraudulent transaction less than or equal to 2 is 0.2 plus 0.15 plus 0.25, which is 0.6. Okay, so there's a 0.6% probability that I will observe fraudulent transactions that are less than or 2 in a day. Okay, so now using this, we can find some. So like we discussed, mean, variance, and standard deviation in the previous video. How do you find the mean, variance, and standard deviation of a discrete uh, distribution like this? This is discrete, right? So the mean for a discrete distribution, the mean is actually called the expected value. Okay, and the formula is given as follows. The formula of expected value is I equals 1 to n xi p of xi. Okay, this is the formula for finding the expected value of a discrete distribution such as 1 over here. Okay, expected value is nothing but the mean. Now if I want to find the variance, I can find the variance as well. Variance of x, this is e of x, expected value e of x, and the variance of x is again sigma I equals 1 to n xi minus e of xi the whole square into p of xi. Look, p of xi here is the probability of observing that value of for xi. So if xi is 1, p of xi over here will be 0.15. So do you see can you see the similarity over here from the formula for mean and variance that we studied in the previous video? So generally, what is the mean? Generally, the mean is x1 plus x2 all the way to xn by n, right? Similarly, over here, what I've done is I have taken the value and I've multiplied the probability. So when I'm multiplying with the probability value of the observation, what I'm basically doing is I'm dividing it. I'm sort of scaling it down for with a particular value of the probability, right? If I have xi over here, which is 0 or 1, and when I multiply with the probability value, I sort of scale it down, right? For to get it in proportion with my probability value. That's exactly what I do in the mean as well. When I take the sum and when I multiply it by n, I sort of scale it down for the number of observations. right? And we know that the formula of variance is xi minus x bar the whole square, whole power n, right? So x bar is nothing but the mean over here. Similarly, over here, e of xi is nothing but the expected value, right? And again, when I'm multiplying it by p of xi, which is the probability of observing that value, I'm again scaling it down, which is equivalent to scaling it down when you divide by n over here. So you see the formulas are very similar. And again, once you have the variance, the standard deviation is nothing but the square root of variance of x. This doesn't change. Okay, so this is a probability mass function. Okay. Now, so I'll just give you an example, just one example, just to drive the point home. If I have the expected value of x, for the same example that I've written over here, the expected value of x is sigma xi p of xi, right? Which is equal to 0 into 0.2 plus 1 into 0.15 plus 2 into 0.25 plus 3 into 0.25 plus 4 into 0.15. Okay, so the expected value comes out to be 2. So if you perform this experiment day in and day out, if this is the values of the probability, on an average over a very long period of time, you will see that the daily fraudulent transactions are 2. Okay, so I've just basically applied the formula over there. And if I have to take the variance of x, again, I'm just applying the formula. I equals 1 to n equals 1 to n xi minus e of xi the whole square p of xi. Okay, so again, if I apply the formula, what I get is 0 minus 2. So we saw that 2 is the expected value over here, right? 0 minus 2 the whole square into 0.2 plus 1 minus 2 the whole square into 0.15 plus 2 minus 2 the whole square into 0.25 plus 3 minus 2 the whole square into 0.25 plus 4 minus 2 the whole square into 0.15. And I get the value of variance as 1.8. So the standard deviation is nothing but under root 1.8, which is it's not 0.09, it's 1.34. Okay, so that's what I've done. This is nothing but, so expected value is nothing but the mean, but for distributions, and the variance, and this is the standard deviation. Okay, and yeah, it's very similar to the normal formula that you know for mean and standard deviation. And why do I multiply it with the probability value over here? Because I want to scale the value over here, this value. I want to scale it down to its value of probability. This is similar to dividing it by n, dividing it by 1 by n. When you take sigma xi minus x bar the whole square in the normal variance formula. Okay, that's what it is. Okay, so now that we know what this is, a probability mass function. And look, you use the term probability mass function when you try to find when you want to find the distribution but for discrete values. But what if it's for continuous values? If it's for continuous values, use the term probability density function. Okay, so the probability function will be given by some value f of x, right? In a continuous value, if you take something like the normal distribution, the function, the probability density function f of x is given by something like 1 by under root 2 pi sigma e to the power xi minus x bar the whole square upon 2 sigma. Right, this is the function for the probability density function. This is the probability density function. Okay, so similarly over here we didn't have a probability density function because I just gave you a table of values. Okay, this itself is the probability density function. Now if you can find a function f of x to sort of, for discrete values, to sort of get these values for some particular value of x, if you can find that function, that's the probability mass function for you. Okay, And for continuous values, you have the probability density function f of x. It'll be something of x. It's different for the normal distribution, is different for the Bernoulli distribution, is different for the Poisson distribution. So that's what it is. So the expected value for the probability density function, which is for continuous values, it's given by minus infinity to infinity x f of x dx. Okay, x is the particular value, f of x is the probability density function. This is the expected value. All right, we'll do some examples when in the next video when we study the normal distribution in detail. Right now I just want to give you the formulas. Similarly, the variance of x is again minus infinity to infinity x minus e of x. E of x is the same e of x that we got over here, the whole square into f of x dx. This is the variance. Okay, e of x is from the mean. Okay, this over here, and then standard deviation again is just square root of variance. Okay, so this is what you mean by the probability mass function, probability density function. Now I just want to explain what the cumulative distribution function is very quickly. So if you have a probability mass function over here, we know from from the laws of probability that all the values that if you extrapolate all these values, if you find you can find the value of the probability on the y-axis. So if you take all the data points and take all of the values on the y-axis, all the probability values in a line, and if you add them, they will all add up to 1, correct? Because according to the laws of probability, the sum of all the probabilities has to be equal to 1. So what I'm going to do is I'm basically taking the sum of the probabilities. Okay, so this is 1, this is 0. What I'm doing is all the probability values over here, all of them over here from here to here, what I've done is I've taken the sum of them and I've plotted them. Okay, ultimately when you come here, the sum of all these probability values will be equal to 1. So that's what I've done. I've just plotted the sum of all the probability values. This is called the CDF, which is called the cumulative distribution function. What the CDF helps you do, it helps you find the probability of observing a value less than or equal to some particular value. Okay, so if I want to find the probability that I'll observe a value, let's say this is 160 centimeters. Again, if we take heights, and 160 centimeters falls somewhere over here. Okay, so the probability of observing around 160 centimeters might come up to somewhere around 0.4. Okay, but the probability of observing a value less than equal to 160, we can get that from the CDF. So it will be the sum of all the probabilities from this part to this part. Okay, and the sum can be, I think, somewhere around 0.78 or something. It can be anything. So that's what the CDF helps you do. It helps you find the probability of observing a value less than or equal to a given value. All right, so I'll see you guys in the next video where I explain the normal distribution.